Greetings. Yes, this is the last video in this series of design and construction of a 10 gigahertz transverter system up on my tower, and I'd like to show you in this video how I operate the station remotely from the shack, control the system up on the tower, and what tools I use to accomplish this. To feed the whole system up on the tower, I use this 48 volt power supply. It's a Meanwell 150 watt 48 volt power supply, to which I've added a volt and amp meter, and also it computes the wattage. By the way, the wattage goes up to 91, 92 watts in transmit. Being a 150 watt power supply, there's enough juice available from this little brick from Meanwell. Another device I use is this box here. This contains the Shack Raspberry Pi Pico. If you saw the previous videos, you know that we have two Raspberry Pi Picos, one in the shack, one up in the box on the tower. This is the Shack Pico, and it controls the IC705. IC705 is the rig I use to control my 10 gigahertz system. I do have an IC9700 that I could have also used to do the same trick. I use 144 megahertz for the IF frequency, so this could have been used. Only problem is, in order to tame the output power, it's more difficult. I send 300 to 400 milliwatts, and that's easily accomplished with the IC705 since it's a QRP radio, but doing the same with the IC9700 would have been more problematic. I would have had to add an inline attenuator in transmit and remove it in receive, so a switchable attenuator, the same thing I have up on the tower. So I decided to leave this for VHF UHF 1.2 gig work and dedicate the IC705 that I had already for microwaving, whether portable or in shack. So this is controlled by the Raspberry Pi Pico. What signals are controlled? You've seen previous videos, namely the PTT line is sensed and the ALC line is controlled on the radio to squelch the RF output until the whole system up on the tower is ready to receive RF power. Okay, so that's the IC705. I don't touch the screen much. I use a remote control software, which you're going to see in a couple of minutes. Another tool I use is this 10 gigahertz monitoring receiver, which we built in a previous video of this series. It uses a satellite LNBF, this orange feed point that I modified to work on 10.368 gigahertz. While this is the interface box in the shack, it's reference locked to 10 megahertz, so I know the frequency I measure is good. The SDR receiver is an RTL SDR. Sorry about the LED, too strong. It's an RTL SDR box, and it's also referenced to 10 megahertz from a GPSDO. So the measurements I make are quite accurate as far as 10 gigahertz frequency received with the LNBF feed, and I'll show you that in a minute. Now let's move to the computer itself, and this is where the magic happens. I use three pieces of software I've written. The first one here on the right is the actual control software for my 10 gigahertz on-tower system. These meters, LEDs, switches, actuator adjust, OCXO adjust, these all read and send messages over the RS485 link up to the Raspberry Pi Pico on the tower, and this is how I can measure air temperature, power amplifier temperature, plus 8 volt, the general bus, plus 8 receive, plus 8 transmit, and RF out. These are the measurement points. I also know if the local Raspberry Pi Pico is sending its status message, and if the remote Raspberry Pi Pico, the one up on the tower, is also sending its messages. I know this because these are blinking. And I also know that the PLL for the local oscillator, the synthesizer chip, is locked because it's green. Right now the system is on, but it's not receiving. Why? Because I have not enabled the received at all. And this is what I'm going to do right away. So by doing this, the transverter receive just came on, and we can see here that I have almost 8 volts. There's a little bit of voltage drop, and that's okay. When I go into transmit, it's the other way around. Receive 8 volt goes down, transmit 8 volts goes up. And this is how I can monitor receive and transmit. I also have control of the fan up there. If I turn this on, the blower, or the fan, the cooling fan is on right now, and it will help bring down the power amplifier and the air temperature inside the box, the enclosure up there. It will help bring down faster. If I do long transmissions, or if it's a very hot day, there is a need for the fan. Otherwise, I can leave it off, no problem. Below here is the actuator adjustment. So you know there's an actuator arm that moves the dish left and right in order to tweak the reception and transmission at 10 gigahertz. And these are the controls I've created. Center, so if I click here, right now the actuator is moving the dish to midpoint control. I can go fast adjustment by steps always. I click and re-click and it moves slowly in one direction. Or I can go very slow by clicking here. You will barely see a movement here. Is the potentiometer inside the actuator, the one that shows the position of the actuator. So it's a read back into the ADC. So it's the actual actuator position, if you allow me to say so. So I can move in both directions, no problem. And I can always come back to the middle with a single click. So that works very well, surprisingly well actually. Just below, OCXO adjustment. So I can tune the OCXO frequency by making DAC changes, writing a new value here, or going up or down allows me to tune the synthesizer frequency. So tune my 10368 transmit and receive. I may have to tweak over time because the OCXO does drift over time a little bit for a given voltage on its control pin, of course. As you know, I've built a monitoring receiver, which I'm going to demonstrate later, and there's a way to adjust and make sure I'm on frequency. The last feature on this box is a CPU reset. So it's the Raspberry Pi Pico up there that I can reset remotely, and I click. I just did. Meters go down, it waits 3 seconds, and pook, system is back up. In case something latches up, I can remotely reset. It's a command. If the Raspberry Pi Pico up there cannot receive any commands, this will not work. I have to power cycle the unit, the 48 volts. But otherwise, if I find there is something suspicious, I can just reset the CPU rapidly like this. Why is there a 3-second delay before I could get the readings again? It's because I added a bootloader. For those 3 seconds, I can upload a new firmware to the Raspberry Pi Pico up there. And it's waiting for the new firmware for those 3 seconds. If no new firmware is being sent, the system is started up. So for me, it's easy to upgrade the firmware up on the box there. Don't have to climb up the tower. Pretty neat feature I've added. And one thing I want to mention also is that the USB port used to talk to the Raspberry Pi Pico, the local one here in the shack, is displayed here. And that's detected automatically. It looks for the UART to USB conversion chip by probing all available ports on the PC. I'm running Linux here. And automatically connects to the right USB port. So this is the status and control software. This is written in free Pascal into the Lazarus IDE. I like Pascal. It was the first serious programming language that I learned back in the 80s, before the C language. So nowadays we can still program, as you can see, with nice widgets like meters. It's available. Pretty cool. Okay, as a helper to send CW Morse code and to turn the antennas, I've also written this software which I call the Microwave Helper. It's basically a tool that allows me to send Morse code in the standard messages that we normally use when doing microwave. So if I click generate messages with the information that's written here, my grid, my call sign, and the other guy's call sign, If I click generate message, it generates these messages here, which are used, like I said, during a microwave QSO. I can always modify those messages if I like. I can type in stuff. Even while sending, I can modify the other messages, no problem. I can also send dashes. When we aim our dishes at both ends, we tend to send dashes. We transmit while the other guy is receiving at the other end, and vice versa. And so sending a constant stream of dashes without having to hold a paddle or a key is very useful, and the tool does it here. I'll demonstrate that in a minute. I can also stop any sending of Morse or the dashes, and I have control on the Morse code speed. And for sending the Morse, I've always used a serial port. I like to control the DTR pin to send Morse code on all my radios. It's universal, and I use an optocoupler, and on this computer here I have a true serial port on the motherboard, and I use the DTR pin to control my radios, and I steer that DTR pin through an optocoupler to any of my radios. So I could theoretically use this tool for any of my radios using that optocoupler and just a switcher to steer this DTR signal to any of the radios. But I've built this mainly for microwave. Now the bottom part of this tool is not Morse code related. It's a helper to steer the antenna by just typing a grid. For example, FN35GS. It tells me what the azimuth is for that Maidenhead grid square, and it tells me also the opposite azimuth for the other OM at the other end. I can tell the person over the phone, steer to 258 towards me. And for me, this is where I steer. And it also calculates, it computes the distance between this grid and my grid up here, of course. So that's a useful tool. If I only enter 4 characters without the suffix, well, it will use the center position in this case FN35. It does FN35LL, which is the center position of that grid, and it will compute less accurate information, but still useful. So once I have written the grid, I can click here and it will send messaging to rotate the antenna. It will actually send the message to this software here, which I'll talk about in a minute. You can also, if you wish, just enter the azimuth you want to go and click to here, and it will send to that azimuth. So that's an add-on tool. It's expected to grow in usefulness. I have room for more things I can add, but for now it's good enough as it is. It does a very fine job. The tool on the left, it's already available on my VE2ZAZ website, ve2zaz.net. This tool is sort of universal. You can go see it there. It's a station-centered orientation tool that can interface with different types of protocols, so different types of boxes. In this case, I use Rotor Easy to my tail twister, high gain tail twister, but it also supports DCU1, DCU1 Plus, and even GS232A, which is the Yaesu protocol. So this tool talks to any smart controller. In my case, I built a controller, and it's also detailed on my V2ZAZ website. So go see there for the controller box for tail twister and for this software here, also written in Free Pascal and available for Windows and Linux. So those are the control and monitor tools I use while I operate. Now, to control the IC705, I use WF-View, which is a Windows and, oh, see that? That's an airplane scatter signal. This is a beacon. It's the VE2TWO beacon. And what you see there is an airplane passing between the beacon and me and causing a reflection, which shifts in frequency, of course. That's pretty neat. You get to see that, guys. So, this is a beacon that's 122 kilometers away on 10.368.380. I use WF-View, which is really a ICOM control software available for Linux and Windows, I believe. And right now what you see here is a beacon. It's the VE2TWO/B for beacon. It's on 10.368.380, so IF frequency 144.380. This is a beacon that's 122 kilometers away from me, and here's a sample sound. So I'd say reception is average right now. It's average. I've seen much better and I've seen worse. We're in daytime and there's not a lot of tropospheric help. 122 kilometers away, still I can always pick it up one way or another. Okay, so this software, of course, I didn't write this. That's available free of charge. You can find it, WF-View. And this is how I control the radio. So this software, along with my control software, and with some additional web tools, of course, like rainscatter.com, that is very useful to see whether we have a path with a station and if rain can help us scatter the signal even better. Very useful tool. I also use w3sz.com, in particular the map feature, which is quite useful. The QRA locator tool at egloff.eu, very useful also to measure distances and to see which exact grid someone is in. So quite useful. We have a Slack group that allows us to communicate, even coordinate QSOs, so very useful. And I also use the Hepburn Tropospheric Index maps. Those are prediction maps, and these help figure out whether there's a potential for some tropospheric ducting, which helps a lot at 10 gigahertz. Okay, now let's do a quick demo of how everything works. Understand that I have nobody to contact right now, but I'll still show you how we normally proceed. My system is enabled, and to transmit, all I have to do is click on send dashes, and now it's sending. Hopefully you can hear those. So I'm sending RF right now, I'm sending dashes, and as you can see, I'm measuring RF output. This is relative measurement. I know that when I'm up here, it's around 10 watts of output. This is the diode detector that's mounted on the directional coupler's output. Notice that the PTT is on and the transmit inhibit is off, and that allows the radio to transmit full power. So when I'm done sending dashes, I can click stop send and I go back and receive. Now I'll bring down the volume here a little bit. So that's, of course, when we want to send dashes initially. If we want to send a message instead, all I have to do is click here, and now it's sending the message. I'll stop that right here. So this is how easy it is. I can of course modify the messages like I mentioned. As I'm sending one, I can modify the others. Those are standard messages, but I can always change them if I wish. Now, in order to steer the thing, I can put a new heading. Right now, as you can see, it's at 88 degrees. I can just enter a new one, say 150, and click enter, and the rotator is going to that heading, slowly, surely, heading to 150. So the software is not monitoring the heading, it's just sending a message. It's up to me to look at this software here if I want to see whether it has gone to the right heading or not. And it has reached 150, 149, 150, which is what I typed in here. So that's in a nutshell how the whole thing works. Okay, the last thing I want to show you is how I measure how accurate I am in terms of frequency. This is the monitoring receiver I built in the previous video of this series, and it uses the LNBF, the satellite LNBF that costs less than 10 bucks. And it's somewhat modified, of course, to be referenced to a GPS DO, so a discipline oscillator. It is disciplined by GPS, so it's very accurate. So I'll be transmitting at 10.368.350, and this is what I'm going to be measuring here at 10368.350. So if I send dashes here, there you go. Here is the signal we're receiving. You can hear it. So it's what? It's about 400, 500 hertz off, which ain't bad at 10 gigahertz, and anyone would find me no problem. Now I can tweak the OCXO if I wish here and try to put it back by clicking on the OCXO value. There you go. Pretty much bang on now. By changing the OCXO frequency, I can tune my system to be accurate. So, if someone asks me, are you on frequency? I know I am. There you go. That concludes my series of videos on this tower-mounted 10 GHz system. I hope you've enjoyed the series as much as I did making it. Now, stick around. There'll be more videos on this YouTube channel. Thank you, 7-3.